Today we are going to study fluid inclusions. You can refer to poll, page number 45 to 49. This topic is also there in ROB, but poll I find poll is better for this particular topic. Now, what are the there are two types of fluid inclusions: primary inclusions and secondary inclusions. Primary inclusions are formed; they are trapped during formation of the minerals. Minerals formed from fluids or solutions, uh, or inclusions may be trapped during in irregularities or on growth planes of the minerals, and that causes inclusions of tiny droplets of the parent liquid to be trapped, and those are known as primary inclusions. And secondary inclusions are those which are hosted by microfractures. We know that fractures are secondary structures, right? After the mineral is already formed, then only fractures can form. So the inclusions which are hosted by microfractures are called secondary inclusions. Inclusions being small, they are very small in size, less than 100 micrometer. Investigations are carried out on thin or thick sections using microscopes. Thin sections are studied under transmitted light microscope, and thick sections are studied under reflected light microscope. In many inclusions, aqueous and gas bubbles occupying 10 to 40% volume are there. Uh, mm, Means inclusions and aqueous and gas bubbles are there because aqueous volume, uh, mm, when the when the fluid is trapped, mineral is forming. That time the temperature is higher, so hot inclusions are trapped within the crystal, growing crystal, and the bubbles that result are from cooling of the hot inclusion when the bubble gets shrunk. So shrinking causes the fixed volume of the surrounding mm, mm, host mineral to have a bubble inside it, because the the fixed volume of the inclusion is it is the whole volume of the inclusion. Within that whole volume there is a bubble which is caused by shrinking of the hot inclusion. Upon heating the sample, the bubble disappears. Why the bubble disappears? Because the volume of the fluid increases, the bubble is not there anymore, and the fluid, the inclusion becomes homogenized, and the temperature at which this homogenization takes place is called the homogenization temperature, TH. In simplest case, TH, TH is the homogenization temperature, is equal to the formation or trapping temperature, TT. What is trapping temperature? The temperature at which the fluid is originally trapped within the mineral. TH is the minimum temperature of trapping, means TH, which is the temperature at which the bubble disappears and the whole fixed volume of the fluid is occupied by fluid only. So TH is the minimum temperature of trapping, since pressure at the time of formation controls size and density of the bubble. We know that pressure changes when exhumation takes place, right? Sample is collected from the surface or near surface or after excavation, so the pressure is reduced, right? From the original pressure may be reduced, right? Now, if the formation pressure is known and the so-called pressure correction can be calculated, the formation temperature can be calculated, right? So we need to know the pressure of formation. That we can do from other investigations, maybe geobarometry, and then the pressure is known, and then calculation is done after corrections, so that we know the formation temperature. For full understanding, the density of the inclusion, its density of fill, What is that? Sorry, it's degree of fill. What is that? Liquid versus total volume. Liquid may be less than the total volume because rest of the volume is occupied by bubble, right? So it's degree of fill. Then the salinity of the liquid. Salinity of liquid, because mostly due to dissolved NaCl, the liquid is mostly due to dissolved NaCl, but there may be some calcium, magnesium, potassium, etc. They are in the liquid, which may also cause some salinity, but most of the salinity is because of dissolved NaCl. The presence of dotted crystals. What are dotted crystals? When the fluid is highly concentrated in salt NaCl, because of the concentration, halide cubes may form, especially when the liquid is hot. When the inclusion is trapped, at that time the fluid is hot. When it cools down, the liquid becomes even more concentrated and crystals form. So halide cubes are common, which are dotted crystals. Then there may be fluid hydrocarbons, and contents of non-aqueous gases may also be there. Among gases, carbon dioxide is the most common gas, followed by methane and nitrogen, etc. So contents of the presence of these are needed for full understanding. What is needed? Presence of dotted crystals, presence of fluid hydrocarbons, and presence of contents of non-aqueous gases. All or some of these are required for full understanding. If all of these are there in some or in different inclusions, then a full understanding uh, can be there about the formation of the crystal, which is known from the fluid inclusions, which can be understood from the fluid inclusions. So investigations must include the identification of groups of associated inclusions that were trapped from a fluid of the same composition at the same time, temperature, and pressure. Pressure is what? A fluid inclusion assemblage, or FIA. Fluid inclusion assemblage is what number of variety of inclusions may be there. So that is called as fluid inclusion assemblage. Minerals contain many different fluid inclusion assemblages, and all these reveal evolution of the hydrothermal system, how the system has changed through time. That can be understood by identification of groups of associated inclusions. Most fluid inclusions observed in hydrothermal ore deposits belong to one of four groups. There are type 1, type 2, type 3, and type 4. What is type 1? Where liquid, what is liquid L, that is there is liquid L, there is vapor, and liquid occupies most of the fluid. You can see the hatchet volume, hatchet part in the fluid inclusion. This whole area represents fluid inclusion. Out of this, a small volume is occupied by gas, water vapor, bubble. So this is the liquid. So most of the volume of the fixed volume of the fluid inclusion is occupied by liquid, and a small part is occupied by water vapor. And the density of the liquid is about similar to 1 gram per centimeter cubic centimeter. In type 2, most of the fluid inclusion volume is occupied by vapor phase, and liquid occupies only a small volume, small part. So most is occupied, more than 60% is occupied by vapor phase, and the density is less than 1 gram per centimeter cube. If types 1 and 2 or types 2 and 3 are cogenetic means which form together at the same time, are cogenetic in the same sample, it indicates true boiling. True boiling means temperature is high enough for boiling to take place rather than effervescence of a dissolved gas like carbon dioxide. We know that when boiling takes place, gases escape from the liquid. So the and effervescence we also know when from high pressure to low pressure condition, when rises up, it effervesces. So true boiling is not effervescence. True boiling is uh, high enough temperature for boiling to take place. Then if type 1 and 2 or 2 and 3 are cogenetic in the same sample, it indicates true boiling of the solution below the critical point or at boiling curve conditions. And effervescence we know when gas like carbon dioxide or methane in water escape from water. Water is the main fluid, right? We know that. In type 3, highly saline, 26.4 to more than 58% salinity with a high density, aqueous inclusions with halide daughter crystals are there. Here you can see the fluid inclusion. Uh, the hatchet part represents the part of the inclusion, and V represents the vapor, and this represents halite. This is halite crystal, this is anhydrite crystal, which are crystals which have crystallized because of high concentration, I mean high saturation of the component, like in case of halite NaCl. When these get saturated, when the fluid gets saturated, it forms the crystals. So fluids of this nature can result from dissolution of evaporites, seawater evaporation, segregation of brines from melt at magmatic temperatures, by formation of residual brines because of vigorous subcritical boiling. Abstraction of vapor causes concentration of salt in the liquid phase, and phase separation takes place. Phase separation means phases like liquid phase, vapor phase, the crystal phase, these are different phases. So abstraction of vapor causes concentration of salt in the liquid phase, and different phases get separated. In type 4, carbon dioxide rich inclusions with little water, at room temperature, carbon dioxide in the inclusions occur in both liquid. Liquid is like here we can see liquid is that of liquid carbon dioxide, and there is vapor carbon dioxide. So liquid phase and gaseous phase in at room temperature, both of these phases occur at room temperature, the liquid phase as well as gaseous phase. Now here let's try to understand this figure. Here you can see uh, temperature in one axis, and pressure in the other axis are shown, and from top to bottom as you go down, pressure depth increases means pressure increases, right? Now this zone, this dotted line represents in lower temperature side there is brittle deformation, and the higher temperature side is ductile deformation. And if we take a look here under this red zone, which I have marked with red, you can see this represents early and very hot brines. You can see the temperature is very high, and these brines are formed at very high temperature. Obviously, initially the temperature is high and temperature falls later on gradually, and if the concentration is very high, hot brine is there, then later on the fluid inclusions will contain some crystal phases, right? You can see the crystal phases shown here. Where's the cursor? Oh, yeah, here you can see the crystal phases, right? You can see the crystal phases, and some vapor phase is also there, and some liquid phase may also be there. In case of brittle ductile zone, transformation zone, brittle ductile deformation uh, transition zone. Here, the later less saline fluids of intermediate temperature are formed, which result in characteristic fluid inclusion. What is the characteristic fluid inclusion? You have a liquid phase as well as a gaseous phase. I've taken this figure from Rob 2005. Even though most of the PPT is prepared on the basis of poll 2005, this particular figure is from Rob 2005. Now, fluids produced in low to medium grade metamorphic terrains are dominated by water, which is the most common, most dominating fluid, followed by carbon dioxide, followed by methane, as in case of any high grade, medium grade metamorphic terrain, right? You know that in metamorphic terrains, medium grade metamorphic terrain, water is the most common fluid. And in high grade rocks, the most common fluid is carbon dioxide with lesser amounts of water and methane. And most metamorphic fluids have low salinities and low concentrations of reduced sulfur. Fluids of this nature are globally implicated in the formation of orogenic gold deposits, which represent a very important category of gold deposit types. We know that gold deposits are the primary gold deposits are formed uh, in orogenic conditions, right? You know that vein formation, veins, gold veins are formed during orogenic process. So that is the most common primary gold deposit, and fluid of this nature are globally implicated in the formation of orogenic gold deposits. Samples transparent to visible light, like a few opaque oxides, sulfides, and sulfur salts. Which are these? These are the most common ore minerals, right? Ore minerals are mostly in the form of oxides, sulfides, and sulfur salts. This can be investigated for fluid inclusions, transparent ones. And minerals like wolframite is uh, mm, uh, tungsten ore, and iron rich sphalerite. We know that sphalerite has solid solution between iron and zinc. Sphalerite is zinc ore. And antimony. So iron rich sphalerite and antimony are transparent to for infrared light and can be examined. Gang are investigated for fluid inclusion studies. This may cause errors in interpretations. Use of fluid inclusion studies. What are the uses of fluid inclusion studies? Great advances of understanding hydrothermal ore deposits. We know that hydrothermal ore deposits have a very large variety, right? And many varieties of ore deposits are formed by hydrothermal processes. So hydrothermal ore deposit formation were brought by petrographic and microthermometric work on fluid inclusions. Petrographic studies, you know, are done under microscope, microthermometric, like temperature of fluid inclusions. Obviously, fluid inclusions being so small, we need microscopes with special attachments, accessories, so that temperature can be studied. So microthermometric work on fluid inclusions can be done, are done, and great advances have been done in this field. It can solve practical questions like differentiation between mineralized and barren veins. Why some veins are barren, why some veins have mineralization. That solution can be obtained, that those questions can be solved through fluid inclusion studies. So fluid inclusion studies are very important. They help in understanding the formation of ore deposits. So thank you very much.